Alrighty. Hello everyone and welcome to Handmade Hero Show. We code a complete game live on stream. What I would like to say today is we are trying streaming from a new location today. The streaming setup has been moved. So hopefully we don't have any problems. It seemed to be solid during the pre-stream. It looks like it's streaming at 30 frames a second with no dropped frames. So hopefully everything is fine. If it's not fine, we'll have to address that after the stream, I guess. So we're just going to go full pull and cross our fingers here that nothing goes awry. If you remember from last time where we were at on the programming front, oops. Try that one more time. Where we were at on the programming front, we had sort of, you know, this is where it would be nice if I was completely caught up on all of the graphics literature. Because honestly, we did something I've actually never seen before. Like, I've never seen anyone talk about this. So it was kind of interesting and neat. We developed a scheme for interpolating lighting that allows us to interpolate lighting on a very low resolution grid but still get perfect spherical lighting fall off. So if you look at our test pattern here, you can see that it appears like we have effectively infinite resolution on our spherical lights. The actual voxel we are using is incredibly sparse. It's like one per like one of these tiles, right? And yet we get this perfect fall off. And that's just because we invented on stream a different way of interpolating the lighting based on signed distance fields that I'm quite sure someone has probably invented before us. We're probably not first, but it was pretty exciting to do it anyway. And so that's where we left off. And using the knowledge of that, what I'm hoping to do now is switch sides, because it, you know, pretty clearly now, at least in theory, we could use this light field interpolation that we've got here to push a lot of good lighting into the system and have it be interpolated. In theory, right? In broad theory, meaning like hypothetically speaking, if we do a good job with it, then we could, right? And the only question is, with this interpolation scheme that we have, how easy is it to actually generate something that can be used with that scheme? So if you know, if you just want to do cheese lighting like we've got in there right now, you can see I'm just literally feeding in 4 spheres. You can kind of see it here. There's a red sphere, a blue sphere, a green sphere, and a white sphere of lighting. And I'm literally just dumping those spheres in and setting the lighting. And what that means is, you get none of the nice lighting effects you would get if you actually do some light transport, which is what we want. You can see, like, the way that we have this set up here, right? You can see that the light transport allows the green sphere to go right on through the wall. So it's not like we've got a point light here that actually is, like, going to get shadowed. And you also don't get any bounce, right? So, a green light over here would bounce off of this, and you'd get more green over here or something, right? So just generally speaking, this doesn't produce any, we're not doing any light transfer, we're just dumping spheres in as test spheres. You can see we can interpolate those test lights perfectly because we happen to know exactly how the light goes. It's a perfect sphere fall off, so it's trivial to put an analytic answer in there, right? But the problem we get now is we need to somehow take light transport into effect, and when we compute that light transport, it's not obvious necessarily how we would go about translating a light transport result, computed at, say, like a number of probes like this or whatever, how we would go about computing a interpolation field of the kind that we need from those answers, right? And so that's really the thing that we don't know, and I'm not sure what we can do necessarily to make that work well. And so that's going to kind of be a open research topic for us going forwards, and I really don't know. What I do know is we've got something usable here. And so what I want to do is kind of flip sides, if you will. We've got like one end of the thing sort of, we have a plausible answer for one of the things that seems to work really nicely, and that I could make a strong argument for it being good, right? What I'd like to do is have some answer now about what the other side of the equation looks like. So I'd like to start working for the next couple of weekends on the upgrading our light transport side of things so that our light transport works and produces reasonable light transport results at light probe points or something, right? So we had light transport working before working on surfaces. That wasn't particularly useful for us because, again, we just have lighting at surfaces. We don't know how to light things like sprites that are standing up on a square. I mean, we could have lit them just from the square, but what we'd rather have is our sprites and everything be lit continuously, just like any surface would be. And now you can see that our lighting voxel in real time is doing that 100%. We just need to feed it with some good data. So what I want to do is flip over to the light transport side of things, try to work on that light transport here so that, at each of these cubes that we got drawn in there, try to produce good light transport at those points. And with a sort of an eye, a squinting eye, if you will, towards how we will output that to an interpolation scheme based on a voxel. And so knowing what we know now about how we can do really good light reconstruction if we magically can turn something into a signed distance field, then we just need to figure out how we would actually compute light transport data at some points that would then translate into a signed distance field, right? And that's really where we're at now. So that's what we have to work on. And it's going to be a while. It's going to take us a while to do that because we have several steps of the problem that we need to really think through and implement, and they're all fairly tricky. The ray casting we've at least already written a version of, so we can at least start with something reasonable with the ray casting. But every other part, we don't really know how we're going to do. So to give you an overview of what those parts are, first we need, at the end of the raycaster, so the raycaster knows what surface was hit, we need a sampling solution. So something that will sample the lighting voxel on the CPU side, for example. We need to write that code. We have a little bit of it written already, but we need to write it better. So something that will sample last frame's lighting voxel and give us back a useful answer there. So we need to do that. We need, because otherwise our ray casting doesn't generate anything, right? We cast a ray, we know what we hit, but who cares? Because just hitting something doesn't tell you anything you need to know about what the light coming back from that hit is, and you don't really get anywhere with that, right? So we need to do that. Then we need to do something that stores the light in the light probes, because what we learned from our experimentation, I'm really glad we did this, from our interpolation experimentation, is you really don't want cubic light samples. It doesn't really work. It's not particularly helpful. So what we'd much rather have, and what we need to sort of work towards, is some fundamental representation of the lighting at our light probes that allows us to reconstruct 3, 4, to our choice, really. At the moment, it's set to 4. Extract 4 different... we want to basically be able to extract 4 signed distance fields where it has a signed distance intensity for RGB plus a normal, a smoothly varying normal. We want to reconstruct those values, 4 of them, per voxel square. And so they correspond roughly to the 4 most important directions of light in coming to that voxel square, you might say. You know, who the heck knows how you want to do that, right? And so if you think about how we might do that, there's a lot of ways we could do it, but it's pretty tough to say. And we don't really even know if that's what we want to do. Like, we may want to end up storing spherical harmonics at these light source points instead, or in the voxel, right? Because that's a more complete representation of the light source. However, you know, again, we don't really know. We don't know if that would have as good visual interpolation qualities. I did check off stream separately, about the thing I was curious about, just to verify that you could add spherical harmonics coefficients together, I was like, if you remember last time I was sort of pontificating about it, I was like quite certain that you should be able to, because it's just a decomposition of the light into basis functions that should be orthogonal. So you should be able to add them, no problem. But for some reason, we weren't seeing that, like obviously listed when we looked at a couple reference pages. So I didn't want to just declare that it was true, but it does appear to be true, right? And so I guess all I would say is we really just don't know going into this exactly what we want to do, and that's why I say it's going to take us a while. We have a lot to figure out, and the reason that we can't just use exactly what we have right now with no thought is because when we're doing ray casting, fundamentally what we're doing when we cast a ray is we're taking a normal, that's the ray direction that we cast the ray in, and we're taking that normal and getting a piece of information back that's like, what is the intensity of lighting coming in from that direction? From that piece of information, who knows what we do, right? We don't know how to store that in any particular way. We can't just store it because we can't record every ray that we cast from every point. They accumulate over time, and we'd end up with like thousands of rays potentially per light probe stored. And what would we do? Like, it's way too expensive to work with all of that data. And so what we kind of need is some way of summing up what all the light that all the incoming light at any given point actually is. And we don't have any way of doing that right now. The reason spherical harmonics are sort of attractive as a way of keeping a running tally of light is because since they are a decomposition of lighting, an orthogonal decomposition of lighting, what we could do is take the decomposition of the light at each point when we do our raycast, and just take that decomposition of the incoming raycast light, add it to the existing spherical harmonics coefficients at every given light probe, and just keep the running tally that way. That is pretty attractive as an option, right? Because it does allow us to sum things together. However, we don't actually know if that's the best way to do it. There are other ways we could be tracking the lighting information at these points. One way, for example, is using some kind of a, like, almost a K-clustering scheme where we would say something like, all right, each time we go to put a light sample in, we look to see if there's, like, we keep 4 actual light directions and 4 intensities, and when we go to add something in, we add it to whatever light is closest, like whichever lighting direction is closest, and we bend the light in, like we bend the normals towards it, right? So we'd kind of keep like a running K-clusters algorithm almost of the 4 light directions and the 4 intensities, right? It's just, who knows? I don't have an answer. I'm as like non-knowledgeable about this as you are. I've never implemented a spatial accumulation lighting scheme like this before. So I don't have any preconceived notions about what we should be doing. I obviously am familiar with some of the literature, so the reason that I think about spherical harmonics is because it's the thing that comes to mind that people generally use when they need to sum lighting like that. And so it seems like the obvious answer in our case. The only thing I don't know is it really the best thing for interpolating lighting? Because, you know, Fourier transforms, which is sort of what it is, Fourier transforms of things have a lot of kind of weird side effects to them. They try to represent periodic functions. They try to represent things that are fundamentally not periodic functions as things that are periodic functions. And I just don't know what to expect. This is where lack of experience is tough. But again, that's the point of Handmade Hero. I like showing how I go about exploring things that I haven't done before, because I think that's the most important thing for people to learn from a series like this. It's not how to do something, you can always go read about how to do something if it's something someone's already done before. The more interesting thing is how do you explore things people haven't done before or slight differences, right? So anyway, if I had a lot of experience with spherical harmonics, I would already know what things I think they're okay for and what things I don't. And so I don't know if I want to go down that road or not, and I don't know if I want to explore other options or not. So it's really just going to be a constant sort of learning mechanism there where I think about it and say, maybe, maybe not, whatever, right? Okay, so I think the first thing I want to do, now that I've kind of jabbered about that extensively, I think I want to break this problem into smaller problems, as I often do when we have something very complicated. And what I want to do is say, all right, we know that we can do 4 light field interpolations really nicely here. I really like the look of that, so artistically, I feel like that's a good mesh. It feels like this game to me. And that's always an important thing to keep in the back of your mind when you're doing rendering, because remember, the point of rendering in a game is not to be accurate. It's not to be what real light does. We don't care what real light does. The point is to look like we want the game to look. It's aesthetics, right? We simulate a lot of the real properties of lighting because they produce pleasing aesthetics, right? Not because we care if the answer is right. Some games may care if there's something specific about them. But for most games, it's about achieving an aesthetic. We like shadows. We like gradual fall off. We like Fresnel. All of these things, they're pleasing to the eye. That's why we put them in there. But it's important not to lose sight of the fact that we put them in because they look good, not because they are real. We don't care about reality in a game. We care about pleasing visuals, or jarring visuals, or grotesque visuals, or whatever the goal of the game is. There's an aesthetic there set by the design, and your job as a graphics programmer is never to produce realistic imagery. Is to produce imagery that comports with the aesthetic of the game. And if that game is supposed to be photorealistic, then that's your job. But if that game is supposed to not be photorealistic, as ours is not, then that is not part of the job criteria. So it's really important to remember that as we go forward. We're not looking for realism here. We're looking for beauty. We're looking for aesthetic comportment with the style of the game that plays nicely with Anna's artwork, that makes its natural richness come out, and not trying to make something that looks realistic, right? That's always important to keep in the back of your mind. So, because I like the way this sign distance field interpolation looks, and it gives me some of that nice cartoon feel, I really like that look, I want to start without the spherical harmonics and see if I can do something without them. If I can't, we might fall back to that as our second attempt. But that's where I'm thinking in my head I want to go. So, going from there, what I want to do is break this up into smaller problems and just see how far I can get on smaller problems. So the first problem I want to do is, let's do direct raycasting of one light and see if we can just produce a version of what we see on the screen right now. Perhaps, let's just pop over really quickly here to the lighting algorithm. Perhaps just one. So I'm going to take, we have 4 lights going in here, right? You can see the 4 lights going in right here. I'm going to take out 3 of those lights. And so if I just take out 3 of those lights, now what you will see is they don't, well, okay, they're still set to their original value. So I really, what I actually need to do is actually clear them here. So for example, if I just go ahead and say light C1 equals 0, light C2 equals 0, light C3 equals 0. If we just truncate those light values so that we only have the first light, and I pop back to the game here, then what you can see is a single light source that's just a sphere. It's placed roughly above the head of the player. And you can see that it actually produces a really pleasing look, but it doesn't have any light transport. So like when I'm here, right, what I want to see is I want to see this be shadowed out here, right? And so there should be some, I want to see some secondary, but I don't want to see any direct lighting over here like I'm getting right now, right? So what I want to do is, let's start with this. Let's add our raycasting back in, which will take a while because we again, we haven't turned that on, so we're going to have to start really thinking about how that works. Let's turn that raycasting on, get the raycasting working. But what we're going to do, instead of using the raycasting to simulate actual secondary bounce transport, we're just going to do direct transport. So all we're going to do is at each of our light probes now, right, we're going to cast a ray from the light probe, just one ray. And the only thing we're going to do is cast it directly at the debug light. If it hits the debug light, we will basically stuff into the light probe the value that we're getting right now, the direction to the light source and the intensity as a distance fall off. So no other light simulation whatsoever, just that. If it doesn't hit the light source, black, no secondary transport, right? So that's the simplest possible thing we could do with the ray tracer, compute a direct shadow. Let's try that and see if we can make that work. If we can make that work, that's a good first step forward, and we'll see what the natural next step is after that, maybe multiple light sources, and we try to start tracking those directions, right? Skip the secondary transport, that's stage 2, right? In order to get to that stage, the first thing I need to do is actually get the light probe to voxel transcription working, which we haven't done yet. So that's actually direct light casting would be step 2. Step 1, or that's step 1. Step 0, if you will, is we need to go from light probe storage, which is basically things that store information in the world, to a screen space voxel that we use for light reconstruction. So that's what we need to do now. Let's work on it. Okay, so what we have here, right, is we've got test light sphere turned on, and what test light sphere does is it stuffs values directly into the voxel. You can see that happening here. It's just a thing. Let me pull it over here so my head's not in the way. It's just a series of lights. We could actually have turned this into a for-i loop. I was too lazy to do that. But what you can see here is this takes 4 light sources here, and it just literally stuffs the values directly into the voxel, right? We also have the ability to set a checkerboard. I don't know if that's still working, but we could take a quick moment to set that up. Here's the checkerboard, and so we turn off test sphere, and we turn on checkerboard. And I guess, yeah, like I said, we haven't actually ported that one yet. So let's port our checkerboard. Let's get that going. So what we need in our checkerboard is just one light source, so probably just this one for the checkerboard. I don't know that we want any other light sources. We can see whether this actually works for us or not. Let me go ahead. I shouldn't have closed the game. I don't know why I always close the game, but because the code reloading would work. So our checkerboard still works. Here you can kind of see an overlay of how big the voxel is, right? It's this thing right here. You can see it clamping out to the values there. So in here, we've got a checkerboard and a sphere like test pattern. That's good. We want to keep them in there. But the actual pattern we need to start working on is what happens when we enable the light probes, right? And what the light probes do is the light probes are the information we store in the scene to get frame-to-frame coherence. So we need we need the light probes to work perfectly. We want them to be able to reconstruct light as well as the other thing, preferably. Now, it can't be perfect because nothing's as perfect as an analytic solution, right? That test sphere is literally perfect analytic light fall off. There's nothing we can do better than an analytic solution for a light source. So it can't quite be that good. But what we like to see is it getting almost that good. We want to get as good, close as we can to that solution. All right. So let's think about how we're going to do that. In our test light probes situation here, right? What you can see is we loop over our probes. You can see we've got compile errors here, and that's because this code has not been ported yet anyway, right? So you can kind of ignore that part for now. But what we want to do in the light probe system is now set up something that's going to map light probes down onto something that we can use for our interpolation scheme, right? Something that will allow us some nice light interpolation. And again, it's not trivial. It's something that we got to think about exactly how we're going to do. But off we go. So in here, where you can see we've got our probe index, what we're doing is we're running through each probe as we go. And we're looking at the probe that's inside a particular voxel. And, I don't really know if this is the best way for us to be doing this right now. To be completely honest, it seems like maybe it's not. But we'll stick with it temporarily because I don't really know one way or the other. What I would say is, now that I think about it, as I'm kind of thinking about it in my head, I almost want to say we just don't want to do this. So let me tell you just based on what I'm thinking here. I think light probes are really not the thing that we want to use, probably ever, for actually reconstructing the voxel. Light probes are just a way of storing the voxel spatially. From frame to frame, we don't have to redo anything. And light probes are places we want to cast from, right? But fundamentally speaking, I think most of what we want to do is think of light probes as just ways of storing information from the voxel frame to frame so that when you come back the next frame, you reconstruct what was in the voxel, right? I think that's mostly what we want. And even as I'm saying that, I'm thinking maybe even that isn't what we really want. So let me suggest something even more ridiculous to you. I'm thinking maybe what we want to do is just lock the light voxel in place. So basically, like, the light voxel stays in one place, and as you move the camera around, it just is where it is, right? And when the center of simulation shifts, so when we move the simulation center from one place to another, what we will do is just copy the part of the voxel that overlaps to the new location, and then the new part of the voxel will just have to get new lighting thrown into it, right? I think that's mostly what we want. Stated alternately, what I think we might want to do is store a large light voxel, maybe one that's significantly bigger than the one we have. So for example, if we go to light voxel, blah, 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 whatever it's called, something here, yeah. So when we look at this stuff, this voxel, wow. So right now we're using literally, it's so crazy how small the voxel is. So right now we're just using a 16 by 16 by 16 voxel. You see what I mean about how good that lighting interpolation was? That is just a really good lighting interpolation scheme. Don't let anyone tell you that Handmade Hero doesn't give you the sweet light interpolation schemes, because we do. That was pretty baller. All right, anyway. So I guess what I'm saying is, if we've got a 16 by 16 by 16 view region voxel, what I'm suggesting is maybe we store like a 128 by 128 by 128 voxel as just like a region around the simulation area where we remember what the voxel values were so that we get that frame-to-frame coherence, right? Then light probes don't store anything. The only thing a light probe is just a place that says, here is some place to cast rays from for modifying the voxel. But it's just letting us know where like interiors of rooms are, right? Or places that we want light information to be. And maybe in the future, we just get rid of them entirely and we just generate those values procedurally. So like any place you can stand, we just spam light vox. I don't know. I don't care. The point is, light probes degenerate to store nothing. All they are is just telling you where to cast. So if you go back and you look at the actual like platform code, right? And in here we kind of go through and we look at the stuff we were actually sending down with commands and all that nonsense, right? So this stuff, this just goes away. The only thing we know is this, which is saying how many places do you want to cast light from. And the really interesting thing about this is if we did that and that worked well, it means we can get rid of light probe index assignment. So we no longer need those indices to be stable either. And how baller is that? That is really baller, right? So I'm loving the way this is coming together. I just don't want to get too excited about it because until we actually have it looking nice with real light transport, you know, it's not over till the trying to think of what the programming version of the phrase "it's not over till the fat lady sings" from opera. It's not over till the high bit is set, right? It's not over till the most significant bit is set. So let's just say that that's the case. So let's just say that we are now no longer going to be using that information. And all we're going to do from the light probe positions is we're going to cast rays. And then inside the lighting system, we will be tracking the radiance and that stuff. We'll be tracking it as the actual voxel. So inside lighting, what I want to see here then is I want to see like our lighting solution. And here we sort of have this light probe irradiance and the spatial probe index and all this garbage. It's just no. The answer is no. We're not going to do it. It doesn't happen. False, right? So this would go away, and we just wouldn't be worried about the probes and where they are in the voxel at all. We don't care about that. We never have to look them up that way anymore. And I love the sound of that, so I'm really hoping that I can actually make that be true. So we nuke that part. And then what we say is in here, we do have a voxel, but the voxel is just the light voxel. So it's actually just this thing, right? And that's the thing that we would use to look up. But we want bigger. We want a bigger version. So we have a large version of this thing, and we're sending down the small version of it, right? So we keep a 128 by 128 by 128. We send down just the 16 by 16 centerpiece of that, right? Or something like that. And that's probably overkill. So maybe 64 by 64 by 64. I don't know. Don't look at me. I'm not a graphics programmer. I'm not supposed to have to know this stuff. All right, anyway. So this stuff goes away. Goodbye. It was nice seeing you, but no. And then we say, all right, in here we have a light voxel cell. And in there we're just going to store the light color and the light normal like we are sending down to the system, but we actually want to keep some number of these, just like this, right? So what we're going to do is we're going to raycast each of the locations in the voxel. And actually, now that I think about it, we may not even really need the light probes. We may just be able to use the lights that are in the voxel cell and cast from their centers or something. So again, don't know. We haven't thought it through yet. So I'm not sure. But chances are we want the light probe still, because chances are we don't want to actually cast from just one location inside the voxel cell, because we'll be too susceptible to voxel cell alignment at that point. And that isn't really good, right? So, all right, just going to start by trying to get this stuff working, really, really basic. Try to have something bigger than the original voxel and where we copy just out of the center. So what we're going to have in here is our cells. The cells are going to be, again, a three-dimensional array, and that three-dimensional array is going to be related to that light voxel that we have, but it's not going to be the same dimension. We want it to be bigger. We want to encompass a larger space. So when we go ahead and look at, like in here where we've got light lookup voxel dim. So where we've got the light lookup voxel here, you can see that the power is listed here. And so maybe what we want here is the like sort of light large voxel. And this is just the larger one. And I don't know that we really need this one to be a power of 2, because I can't think of a lot of reasons why it would have to be. For indexing into the voxel, I guess that would maybe make it a little bit easier. So maybe it is nice to still stick with a power of 2. The reason that a power of 2 is maybe not the most nicest thing in the world is because the power of 2 will never center exactly. You'll always be a little off center, right? If you wanted to be centered perfectly, you would want like an odd number of copies of the voxel. So for example, if you've got 16 by 16 by 16, like we were simulating before, and we wanted to basically have like one cell around in every direction, that would be 3 times the 16, right? And so I don't know if how we really want to do that. Oh, that was Molly's feeder. It's food time for the puss. Does she know? I'm looking at her cat tree right now. She is not even moving. She's just a fully sleeping puss. She was exhausted from the move, so I don't blame her. All right, anyway. So I don't know exactly what we want to do here with that. And so what I guess I'll say at the moment is I'm not going to care. I'm going to use a power of 2. That might be stupid, so we're going to kind of keep an eye on that. Let's put it that way as we go. And what I'm going to say is the light lookup voxel, what we're going to do is we're going to use 2 stops up. So if we're using a 16 by 16 by 16 voxel at actual pixel shader time, then we're going to be 2 stops up from that. So we're going to be 32 to 64. So we're 64 by 64 by 64 on the storage voxel. Okay? That's what we're doing. I have to create it. And it's my code base. What are you going to do about it? Nothing. I'm the only one with write access to the repository. And actually, the repository is just something I mirror to. So even if you hacked my repository, it would just be everyone else who got the wrong code. This machine never sinks downward. Anyway, I hate Git, in case you couldn't tell. Anyway, so what we want to do here is we want to start initializing these cells with lighting data. And what we want to do is when we go to output the lighting to the card, what we're going to do now is output the lighting from these cells to those cells, right? So it's like a copy of the voxel from our internal version to the external version the graphics card is actually going to use. And what we want to do to sort of take this in slow steps is the first thing we'll do is go in 2 waves. So instead of test light probes, which is now not a thing, we're not going to have that anymore. We're going to call it test light transfer. And what we're going to do is we're going to transfer lighting information in. So it's a copy. The probes are gone. So here's our test transfer code. We don't want any of this really. All we're going to have here is the irradiance pack is still going to be there, but otherwise pretty much that's it, right? And then this stuff obviously is going to occur as well. I'm going to get rid of this clearing here because we don't really need that at the immediate moment. But here we have like how we're going to pack this stuff together. What I want to do is I want to assume that I get a light voxel cell back somehow, and I want to pack the data in. So now we've got our light N0, our light C0, right? And we have this, oops, copied. I was a little aggressive there. Oh, did the puss find out that her food went off? I think the puss did. I missed the puss head into the food. I heard it go off. She must have woken, slowly gotten out of her sleep, and done it. I don't know. All right. So yeah, irradiance pack on a light just does the right thing, right? Yeah. So what we need to do now is just irradiance pack our light. That doesn't go in the N channel. That goes in the C channel. We need to irradiance pack our light, and each of these light voxel cells, right, has the data we need right in it. It's got the light. That's what we're going to be tracking. So for each one of these, we pack the light like so. And we say, there's the transfer. The normal is way easier as well, because instead of just like having to pack it down, we just copy it directly. There is no encoding of our normals yet, right? We don't actually do that. It's just this binormal to normal call is the only thing we actually do. So right now we can just set this directly to light n. That may get more complicated in the future, but at the moment it's just that binormal to normal call, and that's all we actually do. So let's go ahead and keep that. So there's us doing the straight copy from the cell, and that's all we need to do for the transfer. The only question is, where do we get it from? And again, here we sort of say, well, all right, we need to, again, keep this centered around wherever the view is actually looking at this particular time, right? And I don't, I wish I had a better handle on exactly how I want to do this. I don't know. So right now, I'm just going to do something that may be a little squinky. It may be, I may be squinking a little bit too squinkily on this particular one, and we'll see in a second exactly how squinked it ends up being. But bear with me, because we're kind of exploring this territory, and I don't actually know what I want yet. And I will, much like Potter Stewart said of pornography, I will know it when I see it. I may just not be able to quite define it. Oh, we got a puss. Hello, puss. How are you doing? Did you have a good lunch? Yeah, I wish I had lunch right now. I wish I had lunch right now. I don't have an automated feeder, do I? I just have to do the stream with no food at all. I have to do this stream with no food. I'm a starving meow. But you got all kinds of good food, didn't you? What are you eating? You're eating that prescription food, aren't you? You're eating Royal Canin? Is that what you're eating? I think that's what she was eating. All right, puss. I got to access the keyboard, though. So is it possible, could you possibly hang out over here for a little while? No? Is that not on the table? Is that, puss, I gotta type in some code, baby. Is that okay, Molly? Can I code some stuff? We have a bit of a puss situation here. I don't know what we're going to do about that exactly. She likes to type on the keyboard. Okay, so she's just basically sitting down at this point. So I don't know. We're going to have a little bit. We might have to try and type around the puss. I'll try to type around the puss, but we'll see. She's basically sitting on the wrist rest now, so you know how it is. Those of you with cats at home will be familiar with this situation. They like to be where the action is. They don't necessarily understand the fact that you have work that you're trying to do, but we'll see. All right, so anyway, inside here, if I grab out my light cells and I pack them down, then the question is just where do I get them from, right? So if I have some kind of an XYZ, okay, now the puss is stepping on the keyboard. That's good. Let's just keep going. There we go. So now she's going off. All right. So if we take a look at the XYZs of the cells that we actually have here, you can see we do have them. The problem is they're just not in a particularly good location for our offsetting, right? So what we probably want to do here is we just have like a Z offset, a Y offset, or something like that. Oh, okay. There's some puss typing. Okay, you're sitting on the delete key, baby. That's going to be bad. Okay, we don't, and the tail right now is going like literally right along the prime part of the keyboard. Molly, baby, could we possibly move you to the seat? Do you think that's a possibility? What if we just, come on, baby. What if we just moved you right there? Would that be a good place? Do you want to sit down there at all? I don't think she likes that seat very much. What do you think about that? What do you think about that seat, huh? Do you like that at all? It's probably not warm enough, huh? All right, she's going. Okay. So, when the puss comes, you just got to deal with it. That's just part of programming. A lot of people ask me, like, as a junior programmer, what should I be focusing on? The answer is your cat skills. You should be good with cats, especially if you're ever going to work with me, you got to be good with cats. Okay. So light voxel cell, we've got a Z, Y, and an X here. And if we were just looking in the bottom corner, that would be fine. But what we actually want to do is we want to look at some portion of our larger voxel that's where we've decided we are. I don't want to have to do anything fancy here, so I'm just going to do like the sort of like hot Z, hot X, hot Y kind of a thing, where we basically say we've got some portion of the voxel that's sort of the interior part we care about, and we're going to offset our larger voxel by that voxel, right? So this is just a transfer from one voxel to another, and that's all we're doing here. And so what I'd like to do now is just have a way of initializing our larger voxel, maybe with the test sphere, and then verifying that that can actually be copied in. So let's say that I do this here, and we, in fact, I just literally want to do this. I'm going to loop over the large voxel, initialize the large voxel, and then from the large voxel go to the small voxel, right? That's all I really want to do. All right, so if I was to literally just cut and paste all this code, right? So I'm literally just going to cut and paste this entire thing. Although I guess I only need one of them. We're only dealing with one light, so I'm going to do that, right? So what I want to do here is I want to store, and the light C0 I want to actually, again, keep as a full light value now. So this is not going to look like that. Instead, what we're going to do is take the actual like V4 we would have packed down and keep it, right? So that we have what I think is the correct settings here. And then when we go to pack it down later, we'll pull that out of it. So again, gotta go through this with like a finer tooth comb than we are at the moment, but basically what we're going to do is we're going to insert into our larger voxel the smaller voxel information here, right? And when you compute vox center P, I now need an offset that's like the hot voxel P part of that, so that's moved up. So when we compute this stuff, right, where we do, trying to explain this, we have a small voxel inside a large voxel. I should probably draw this out for you, but I'm too lazy at the moment. We have a small voxel and a large voxel. The small voxel is some cutout of the larger voxel. We now want to test that we can copy things from the small part, from some subset of the large voxel to the smaller voxel. So what I want to do is initialize the entire large voxel with the distance to the light. So this will basically be, something like this. Right. And that's all we actually need. Oops. So we just want to initialize the whole voxel with that light. The problem with doing it this way is we previously said where the light was in UVW space, which doesn't necessarily help us. You can see us doing that computation here. So the Vox UVW, like this computation is kind of useless, right? Because we don't actually know where the light is. This is telling us where the light is in the small voxel, but this is the large voxel, right? So while it's easy for us to tell what the UVW is in the large voxel, it's not easy for us to tell what it is in the small voxel. So we kind of want to make this work a little bit more broadly, and we want to start talking about where this stuff is in actual real space. So we're getting, like I said, we're going to have to grind a little bit and get all this stuff working in a slightly different way than it was working before. But the good news is, like, hey, this UVW stuff was just things that we were sort of pre-computing for using the in-voxel dim and this kind of nonsense. So what we can do is start to just work back towards the world space. We had those values already. Those were these like light P, light P2, light P3, light P4. Those are already in world space. So what I'd like to do here is say we've got a Vox center P, and I'm going to compute that as an actual location. The Vox center P is going to be a offset. So if we said like Vox min corner, we had that value, and then I added an offset to it that was the amount sort of the voxel, scaled by whatever the voxel dim is, right? So we have some notion of the minimum corner, we have some notion of the cell dimension, we scale that out, and this is where the center of our voxel is now in world space. Then we get rid of this. And now when we talk about our light normal, it's just going to be the light P minus the Vox center P. The rest of this can stay the same. Now we have a little bit of an issue here because you can see we've got a light color that's going to be the fall off here. That fall off needs to be broader, right? So it needs to be more like, like that or something, where it falls off at like a 4-meter radius or something like that. Maybe even a little bit more than that, 8-meter radius, I don't know. Who knows, doesn't matter, but it's something, right? Then we've got our light intensity, and the light intensity is, again, just something we use to figure out how bright the light's gonna be. That can stay the same at the moment, but we'll play with that later. And now we've got something that will go through the whole world space of this sort of voxel, initializing it to be the correct values for this one light source that we're tracking. Then we go through here, we get rid of the probe stuff, we go through this and we say, all right, when we do the light transfer, we pick stuff back up out of the voxel based on just that center point. And you can see that happening here. We copy it in, and that's the part that now we're trying to get right. Okay, so let's move towards that. First thing we need to do is actually put those values in there. So if you take a look in the lighting solution, we've got sort of this information here about the voxel that we commented out. We now need to put some of that back in here. So for the cells, I want to do the Vox min corner and the Vox cell dim. That's how we're going to map from the voxel back out, right? We're also going to need the im cell dim. So all that stuff basically just needs to be known to us. These two values are the same, but what we probably want to do is be a little bit careful about how we're naming these things. These two are the same, so they are the voxel, like the cell dim and the inverse cell dim. Those are correct, no matter which voxel you're talking about, because our voxels line up, right? The small one is just a subset of the larger one. So you only ever need to talk about one set of dimensional values, right? The cell dim and the im cell dim are the same no matter which voxel you're talking about. But in this case, we actually have two. So we have a Vox min corner for the large and a Vox min corner for the small, and they're not the same, right? And we similarly that like hot min corner, maybe we'll call it the hot location. So we could actually say this hot XYZ So we kind of have a voxmin corner hot, and then also a voxmin hot corner I. That's the index of the hot corner inside the large voxel, right? So that's roughly what we need to track through the system in order for it to work properly, right? We're going to need to set those up. And then let me start cleaning up compilers now so we can start to test this out. So this stuff is no longer with us. It was not long for this world. We thought we were going to need it. We didn't end up needing it. It was just something we played around with. In here where we do the spatial index, again, don't care. This stuff, similarly, don't care. So when we go through the light probes now, oh, well, actually, that's fine. So the light probe P's we may still want, but those are just going to be kind of directly used without that voxel part. So we'll keep those temporarily because I think we may still want those. Okay, so if we go to the spatial index here, this stuff we don't actually want, so this needs to stop, and this we now will have to reckon with how the transfer, like this is going to end up being a voxel lookup. So it's going to be a get probe lighting based on a position now, so it's kind of a separate thing we would be doing. Let's just do this. All right. Who's next? So all of this code is just not a thing anymore, right? So these are just completely zeroed out. Like all of this stuff is not a thing. And we'll delete it as soon as we are sure we don't actually need it. So in here you can see where we are initializing the spatial probe index. What we probably want to do now is actually initialize the rest of our solution stuff. So when we go in here and that's not what I want to, there it is. When we get all this stuff, all of this stuff has to kind of be initialized. This stuff will vary per frame. This stuff won't. And so what we should be able to do is just set these here, right? If we want to. I'm going to let it vary per frame probably. So what I might do is say, look, we'll take that over here. So when we begin the lighting computation, if every frame you wanted to vary it, you could. And off you go, right? I'm not sure that's the smartest way to do this, but all right. And yeah, so now we just kind of need to deal with exactly how the light corner stuff is working, and we'll talk about that a little bit, a little bit later on, because there's a bunch of stuff we have to do to make that work properly. But yeah, this stuff now can go away, and now we really just need these two. And this is all stuff we're going to have to actually fix. So like what we need to do now is we need to take the lighting bounds and regularize them. So instead of when you call begin lighting computation, you're no longer going to be able to call begin lighting computation with an actual bounds. You're going to have to call begin lighting computation with like a center point or like a viewing point or something. And when we change the camera location, we have to update the lights as well, right? So the lighting system will now have to be camera aware, and it has to do transfers that will like be able to copy parts of the voxels around, if that makes sense. It's more complicated than what we were doing before, but way better. Like, this will prevent us from having to do a ton of the work we were doing. Like, we won't have to translate to and from light probes anymore, and the values that we copied to the graphics card are the same values we'd be tracking and all that stuff. So this is just way better. I think this is what we should have been doing. So yeah, getting rid of the light probes seems like a great idea because there's just no need for it. And it also means that the entities won't need to have light indexes assigned or anything like that because we'll be keeping track of the light spatially, not in terms of probes, and that just seems strictly better to me. Yeah, so I think that's all just better, and we'll go from there. All right, so we have a ton of stuff to do now to get that going. I think probably my goal for today, because I have like maybe what, 20 plus, so 30, I have maybe like 35 minutes. So I think of what I want to do today is I just want to go through and try to get the voxels tracking properly. We probably won't be able to actually get to the point where they're actually running properly just today because there's a lot of plumbing that has to happen. But clean all that stuff up, and then tomorrow our goal will be to get the light voxel reproducing the same effect we have today. And then we are really in good shape because at that point we are ready to just do ray casting and go from there, right? And I think that'll be really pretty easy. We're even ready to sample. We can sample the lighting trivially at that point too. So yeah, I think that at that point it starts to be really good. So that's our goal for this weekend. Get most of the plumbing done today as much as we can. Tomorrow get it working, and then at that point I'm a happy camper because we'd be in really good shape. All right. So let's push through. What I want to do is now kind of go back and go to the outer code, fix a little bit of how that's working, and we'll go from there. So inside the world mode, what we have right now is like the camera, right? It updates in a number of ways. So when we actually find those light bounds, you can see me looking at the light bounds here, right? And you can see when we do begin lighting computation, what we do is we say, we tell the lighting system where the light bounds are. And the part of the problem with that is the lighting system doesn't really know where the light bounds are in absolute space. This is just telling it kind of based on the random like location that's it's based around the simulation center. They're not absolute coordinates, right? And so I think what we'd want to do here is say, all right, we've got the world camera rectangle that we produce from the render group here, right? And that is sort of well, it's not really that useful. It's really not that useful. What we would probably rather have is actually like look at what we're using for the camera's absolute center. So, when we're actually doing the camera, pulling the camera information out here, where do we grab that? Render group, no, this. So where we actually look at the world camera P and the simulation center P, like that difference going on here, right? I think what we actually want to do now is the camera P is like where we are. And we know we can go from that some distance forward and know that that's like roughly what we're focusing on because we do have a focal point. Like we know roughly how far away we are from the camera in terms of what we're trying to look at. And so I think what we want to do is actually just ask, or rather tell the lighting system that. Like that's what it should actually be given. So I think instead of light bounds, which I don't think we want anymore, I think what we want is more like, here's the camera position, right? And since this lighting has to be stable, we're going to tell you the camera position and one other piece of information, which is how far away we expect the camera to actually focus on, right? So you can see the focus Z kind of comes in here. And so we may need more information than that, but you know, we'll say we do something like this at the moment. And then what I'm going to do is say, all right, that camera rect, does that actually get used for anything? Because if it doesn't, then we're going to toast some of that stuff now. Yeah, so all this stuff now I think we want to kind of get rid of, right? And we need this to sort of be a value that we tune because we need the lighting to now be stable. We don't want the lighting sampling points to shift around. So we want to just pick the largest volume we need to light, align to that, and that's the end of it, right? So we then say, all right, all of this stuff I think goes away. Well, no, it doesn't. So the simulation bounds are based on the camera size? What? That just seems totally busted. I don't want that at all. Wow, okay. So I don't really want that, and I don't know what that is doing there. So I want to start eliminating more of this code, actually, quite a bit more. So we're going to organize this a little differently. World camera rect is going to get pulled out, screen bounds, so on. So sim bounds we want, but that's literally just going to be this. All of this stuff I don't really want happening anymore, including this. So I don't know why we were still doing that. I feel like we should have removed that, but I guess we were trying to be squinky. I don't think we should have been squinky like that. I think that was a bad squink. So I'm gonna nerf all of those and clean up the results because I didn't like that. That was giving me a bad vibe, a very bad vibe. All right, so we're gonna deal with the fallout from that in a minute here. We don't need this. Don't need any of this. And this is the large corner specifically. This is a Handmade product. I'm not sure why I wrote that as a standard product, which we don't allow for vectors, specifically because it's ambiguous. Which kind of product did you want? Handmade product, dot product, cross product. Here it looks like this is a little weird because that should have just been a multiplication so that we had the red, green, and blues all equal channel there. So don't ask me why that was looking like that. It was just a holdover from when I did the copy pasta there. This is just needs to be an address of. And now I think we're good. So in terms of the focus Z here, again, I'm not really even sure we need the focus Z, so maybe I won't even use that because we really need this voxel to be stable, so I'm not sure we can afford stuff like the focus Z. We probably just need it to encapsulate the frustum reliably. So we'll see. All right, so let's go ahead and jump to begin lighting computation. And now the big change here is instead of a rectangle 3, this is going to take a world position. And that's the location of the camera. All right. So now what we have to do is we have to work backwards, right? We have to now like figure out how we're going to make this voxel be properly aligned with our view. Now, in order to make sure that we have lighting that kind of covers the region that we want, obviously, you know, you figure we got to push this thing out along -z a certain ways, and so on, right? And furthermore, with the world position, with the camera P here, we also need to know the simulation center because that's like the coordinate system center. So in order to get that information, we also need to produce like, let's see here. Where is that information actually? So I guess actually the simulation center is always at 0, 0, 0, but we just need to know, yeah, you can see here. So we actually have the delta from sim values. So actually what we probably want to do is maybe something more like this. We would tell it where the simulation center is. Or like that. And where the camera is relative to the origin. And those are the two things we would pass. Because the simulation center is 0, 0, 0, so we want to know where that is so that we have the correct relative positioning for everything. So we'd actually want to do this. And then we would have delta from sim. And you know, delta from sim just tells us where the camera is relative to that simulation center, right? And so what we want to do now is say, all right, the world origin P is sort of a way that we would track where we line everything up, where the voxel is and all that sort of stuff, right? And so there's a lot of different ways we might want this to work, but generally speaking, what we want to do is think about the voxel getting updated over time. So when we do begin lighting computation and you tell us the origin P, the first thing we want to do is kind of move the existing voxel data, copy a subset of the voxel data, and clear the rest of the voxel, if you will, so that we're like shifting the voxel around in like a locked fashion with the motion of the simulation in the camera, right? That's what we pretty much want. Now, thankfully for us, we don't have to care about that stuff yet. And the reason that we don't have to care about that stuff yet is because we are just trying to do the basic operation of computing the lighting on a single frame. So we don't need... hello, puss. Hello. So we don't really need any particular frame-to-frame coherence, so we can skip that for now, but this is what we will need to carry forward with us. And similarly, when we look at the voxel dimension stuff, that stuff... Okay, puss, can we just not... Okay, thank you. Okay. Yeah. So when we want to compute the rest of this stuff, we now need with this like the set light bounds as well. I'm not sure what that's actually. Oh, so the set light bounds. This stuff is important to tell the pixel shader like what's going on. So we need the min and the inverse light dim and all that stuff. So that's the stuff that we need to get right at this point, right? So let's go ahead and compute that stuff stably. So the first thing I want to do is say we know that the cell count for the small voxel is this, right? And so we know that we want to set the dimensions for the light to be something based on that captures the size we actually needed to capture. And this has to now be hard-coded. So we can more or less just well, it doesn't have to be hard-coded. This has to be stable. So we can now just hard-code it because it can't change frame to frame. Or we would get, like, you'd see visible artifacts if we were changing where the light information was stored from frame to frame. So what I want to do here is say, well, the lighting dimension is therefore going to be like computed this way. The light dim is, in fact, I guess if I look at light dim, I just need cell dim though here, right? So if I look at the voxel cell dim, what I want to do is say it's the cell count, right, times the cell dimension, or rather this is that, so I guess I don't need the entire light dim. So what I want to actually say here is this. And I guess I'm not sure, why do we have a thing that both enables the light bounds this way and then does it this way? I'm not really sure. Again, we can clean up, I think we can clean up the pipeline a bit once we get all this working, because then it will be absolutely clear what actually needs to go down to the graphics card and when. So we'll be able to simplify this a bit. Anyway, so when we do begin lighting computation, we've got our solution flowing in here. Assuming the lighting is enabled, we've got our cell information producing here. Our cell dim is just going to be some value that is hard-coded to produce a large enough, a large enough size. I'm going to start with 2 meters per voxel, and we're going to see what that translates to. That may be too big. I don't know what the size of the voxel was before. Maybe we'll start with 1 and we'll kind of go from there. We'll scale it as necessary. Maybe it should be 2. I don't know. So then we need to figure out like where this thing is in terms of the sort of where the actual voxel is in space. And again, we need this to be like locked to the voxel cell dim. So we need it to be spatially coherent so that it's basically truncated, right? We don't want it to have, we want it to be so that it moves an entire voxel cell at a time when it moves. So we need the large voxel and the hot voxel to be like aligned in that way. So if we look at how we're going to do this part here, and we'll construct the light bounds in a second here. This is going to just be this. I guess we don't really need to do that. I don't actually remember what we had for our V3s. So if we look at what we would use to construct this, it's like a rectangle dim, right? Like it's a rect min dim. So it's rect min dim, oops, and it's specifically the 3-dimensional version. So it's this. So the light bounds is going to be reverse constructed now. So instead of passing it in, we're going to construct it from the voxel. And we're going to say that it's the light dimension, which is this Hadamard product here, whatever the cell count is times the voxel cell dim. And then the minimum value is just the that hot corner, right? So then what we have to do is figure out where this goes, right? And this is relative to the camera, but again, then truncated based on its sort of divisor, right? Now, the vox min corner large is easier because that is literally just an offset from the hot corner. So this is literally just like, you know, a displacement, and it's specifically a displacement of the cell dimension times however, you know, whatever that hot corner value is that's like the offset inside our larger voxel. So, you know, if we look at what we've got here, and we've got like min corner hot, min corner large. This hot corner I is the thing that says how many voxels squares you go to get from the large corner to the hot corner that lives inside of it. Right? So it would be this. I don't know if we have a V3. Converter for V3Ss. I must just say we do, and if we don't, I'll make one. So we have a Handmade product. Between those two, and I think that's it. All right, so obviously our voxel dim, I don't know why I didn't set this to an actual full vector. Obviously it is. This is supposed to be, yeah, the min corner hot. It's actually an offset that way. In this case, it looks like hot corner I just was missing its access pointer. What else you got for me, compiler? Yeah, so the cell count is not an actual vector, so that's a bit of a screw up there. So what we actually want here is the cell count. In cell count really doesn't need to exist, I guess. And so in this case, the cell count doesn't vary over the voxel. So we're really just lofting it to a F32 and multiplying it by the dim, right? It's just a scalar multiply. And then in the light dim, we don't really compute at this point. So we would need to. Oops. So we're looking at something more like that. And so the only thing we really need to know now is where actually is the lighting relative to the camera. And it's kind of a little bit tricky to figure out where that's going to be, obviously. But again, what we need to do is we need to determine like what that value would be locked to a world space coordinate, right? So if you take a look at the origin P and then you look at the camera offset from origin. So the problem that we have now is we need to like make sure that the camera offset in actual like literal space, we need to make sure these voxels don't shift around, right? Now what I would like to say, so if we take a look at the world position, right? Then inside where we actually determine the world position information, you know, we've got a value in here that's like chunk dim in meters. And if we look at what that is set to, right? Create world. So I want to look at where we call the create world call. Here it is. So if you look at where we set world chunk dim in meters, you can see that like the actual like sort of stepping of the world in integer coordinates ends up mapping down to like sort of roughly like a room-ish sized area, more or less. So, you know, we don't probably want the lighting voxel locked. Well, maybe we do. I don't know that we really want the lighting voxel locked to that. I mean, maybe we do. but it doesn't seem good. So the problem that we're going to have here is we have to figure out how to produce an accurate locked light value that's truncated. But that's actually pretty tough. So the reason that this is difficult, right, is because if you look at what we need to compute, coming into this function, we have an origin p-value, which we can turn into a full float if we want to. But the problem is it will lose precision when we do that. So we need to figure out is where should we be? Like we almost need to know what the low bits are of the thing, which is tricky. So I got to think about how we would do this. That's a tough one. This is something I wish I wasn't so hungry. I'm very hungry right now. I don't think very good when I'm not eating. I feel like this demands like at least some peanuts or something. Hold on a second. All right. So the problem that we have, let's crunch on some peanuts, shall we? Much better. All right. So the problem that we have here is the thing we want to compute is we want to take origin P plus the camera offset from the origin. We want to produce like a V3 from those. And then we want to divide by the voxel cell dim. So multiply by im voxel dim basically, right? And use something rounded to that as a whole number, right? We want to align this to a whole number multiple of the voxel cell dim in space, right? And the problem is, if we literally did just the steps I was saying, we would lose precision in our floats. So we can do this a number of ways. One is we can just do the computation in doubles. We could. The other is we have to work out the math to compute the value we actually want without ever actually explicitly creating the values, right? Hopefully that makes some sense. So I think we're going to need the whiteboard for this. I don't know if I can do it in 10 minutes, but I'll try. And we'll see where we go from there. I gotta remember to have some peanuts on hand for streams in general. All right. Problem solved. So, I neglected to test the actual Wacom tablet when I moved the setup here, so this may not even work. It looks like it is at least nominally plugged in, so that's a good sign. let's go ahead and open up Milton here. So, Milton. I don't know what I want to call this. Wait, how is it day 563? Is that really right? Hold on a minute. Is that wrong? It's a little late now. But is that wrong? Yeah, that's totally wrong. How did we end up? This is day 566, isn't it? Anyone? Isn't it day 566? Does anyone know? I'm gonna leave it as that. If somebody knows what day it actually is, please tell me. All right. I think it's day 566. Better? I think so. Like, what was it up here? So that was day 564, right? So if that was day 564, then it certainly can't be day 562 or whatever we had on there. That's like totally wrong. All right. So we need to align our voxels. And what we've got here is we have essentially a problem of one set of grids. Oh, wait. There we go. We have what amounts to one set of grids, and we have another set of grids that we want on top of those sets of grids, and we want to make sure that they always line up, right? Not these two grids, but this grid that operates inside of this other grid. We want to make sure that they always line up like that, right? So, or like this or whatever. We never want two voxel, like we never want our voxel to be like here on one frame, and then the simulation center shifts, and on the next frame, it's like that or something, right? So we always want cells to have their centers in the same places, and we just shift the voxel around. So from frame to frame, we may move, it's like there on one frame, and on the next frame, it should be like exactly there, but one cell over or something. But it always should move on multiples in some way like that, right? Okay. So the problem that we have is we are working off of some, we're working off of some center point where that center point is not the same size grid, right? So if I actually bring up the grid size here, let's suppose the tile size is really big, right? So like here's the world grid, and then our voxel grid is like this tiny grid inside there, right? It looks like that. Does that make sense? And we're trying to align to this, but our coordinate system is based off of like the center of like this, right? And that makes it really difficult to reason about, because if we're trying to align to this grid spacing is unrelated, right? We don't start off being aligned to this grid when we're at the center point of the other grid. If we were, we'd be done, because we'd just align the camera offset vector and be done, right? So our problem boils down to, given a world position, right, which remember is like written in the form like index x index y, index z, right? Hadamard product with the world chunk dim, so chunk x, chunk y, chunk z, right? This is the like index, this is the chunk dim. So the Hadamard product here of these two gives us what we want to know about the center point, perhaps, of this, right? And if I'm not mistaken, is that the entirety of it? Yeah, so you can see here, like when you subtract two of these positions, right? All you really do is, and when you look at the offset as well, right? You can see recanonicalized chord. So I don't really see anywhere where we make any other assumptions about the world at all, honestly. So all we really know is that we have a world chunk dim in meters. You can see we literally are producing this. And we want to make sure that the thing that like when we come out of this, we're going to have some position like here. And we just want to know what the closest thing would be aligned to our voxel grid, right? So we basically have another thing here, which is the light like dim, the light cell dim, right? And this is the chunk dim. So we have like an LX, an LY, and an LZ, right? And what we want to know is after we do this multiplication, we want to know our relative standing versus the light voxel. So we want to be able to round it to the nearest one of those, right? So if you wanted to know, I times c, because this is entirely scalar, right? So we don't actually care about the fact that these are vectors at all. This is a completely separable thing. So if we take I times c and divide it by L, right? This value is going to tell us which cell we're in the light voxel in absolute terms. And all we really want to know is essentially the modulus here, right? So what we really want to know is what is I times c mod L, right? That's what we want to know. Because if we have that value, then we can solve the problem. Because then we know how far we are from the part of the cell that would be perfectly aligned with our light voxels in world space, right? So I mean, since this is just a multiplication, presumably it's more or less going to be the same thing. Like, if you imagined that this was a divide instead of a modulus, right? Then what you would expect to see is you would expect to see I times C divided by L could be factored separately as I over L times C over L, and you'd get the same, sorry, that's not correct. Trying to think of how I would factor this, because it would just be I times C over L, right? I mean, that's all you would see. So, trying to think of, what I could do here that wouldn't have this problem. You'd think in all these years of programming I would have had some time when I wanted to factor a modulus, but I've never done that before. I mean, I can certainly add more stuff in here, right? So like if I wanted to, I could factor it as I over L times C over L. And what I would end up with is ICL squared at the bottom. So if I wanted to, I could just knock out an L, right? Meaning this L over 1 here. So if I do I over L times C over L times L over 1, that would give me the factored version, right? That multiplies to this. So if it was a divide, if I just want to know what the divided number is, I can break it apart. And if I broke it apart, each one of these terms can be dealt with separately. And I know this one is safe. And I know this one is safe. And then this one I could guarantee was safe because I could make sure that this value was an integer, right? I can totally make, like right now I was thinking that it would just be 2, right, was what I think I put in there. And then this would be safe as well, right? So if I want to do a divide, I certainly can. The question is just, how would I recompose the modulus? Because a modulus and a divide aren't the same thing, right? So this tells me what I need to know for how far I don't really see that really tells me much of anything at all, right? So I'm curious. That's not really what I wanted. This looks like what you would want. Of course, I don't know enough math to know whether I should trust the math version of Stack Exchange. The programming version of Stack Exchange is pretty risky, but and these are additions. So I really want just a concise statement of the of which options I really have with modulus, right? Isn't there something from Math World or something that I could use here? This is not... Well, okay, maybe it is sort of. I mean, yeah, I mean, you could phrase it in this way, right? So if A times B mod C is the same as A mod C times B mod C, then we certainly could phrase it that way because we do have that. The problem is I'm not 100% certain that we actually get much out of that. Because, again, you can kind of see the nastiness here, right? Like, if we have A times B mod C equals A mod C, I did that right, A mod C times B mod C, right? If we're doing that, then the problem that we have is, let's suppose we break it up that way. It's pretty easy for us to say, well, it's the index and the chunk mod the L, right? And so here we would just say, well, index mod L times chunk mod L mod L, right? And that's fine. The problem is this, we still don't really know what to do with. Oh, well, no, it's okay. So, all right, no, we're fine. Thank you, Khan Academy, for having that as the first thing on the page. I do think that's fine, because if we think about what's going to happen here, these two both are going to be just the modulus that we've done, right? So if we do I mod L, we will get a small number. And if we do C mod L, we'll also get a small number, right? No matter how big I and C were, we should be fine there. And so as long as this number we know is small, and this number is small, and this number is small, and that number is small, this is the only number that could be quite large. So as long as we could compute the modulus of that easily, then I think we're okay. And so I think all we need to do is make sure that the light cell dimension is an integer, right? If we just make sure that the light cell dimension is an integer, we should be able to take the mod very easily. For example, if we did pick a number like 2 or 4, right, then we would be able to do the mod on the index for the chunks. We'd be able to do that directly. We would not need to ever actually compute it, right? We could just do a straightforward bit operation, because the mod 2 or the mod 4 or whatever of any power of 2 value would just be the bottom bits of the number. So we know we wouldn't have any numerical stability issues if we just take the bottom bits of the number. And we know that there's only a few. So we take like the 2 bottom bits of the number, and we multiply that by the actual modulus of C times L, of C mod L, right? That would give us another small number that could then be mod L. So I'm okay with that, right? If we were to say like it's 2 or something, right? Then when we want to take this modulus, we take a look at the origin P, so in world position, right? And it's got this like chunk X, Y, and Z. So if we were to just look at those base values, I have to think about what happens with those values when they're negative, because when they're negative, then the low bits may need to be like flipped in order to get us the right value. So I'd have to think about that. But otherwise, I think we're okay. So what we want to do here is say, yeah, like chunk X, Y, and Z. If we just look at like what happens with chunk X, for example, and we say we need to know the mod of that for a 2 wide cell, right? Then all we should have to do, I argue, is just take the inverse of like whatever the bottom bits are, right? And out the rest, so and out the top. So for 2, I think we just do this, right? That is the mod of of that index, right? So then we need to know what the modulus is. Don't we have a modulus? We must have a modulus somewhere. We've never done a floating point modulus. There's no way. That can't be true. Seriously? Huh. All right, well, we'll have to get that in there tomorrow as well then. So we would need the modulus of whatever the actual world size is as well. So we would need that where are you? There it is, chunk dim in meters. So we would need the chunk dim in meters, and we would need to take the modulus of that with respect to the light as well. So we'd basically need a mod 2 of the chunk dim in meters. And then we would need to take the modulus of the whole thing, right? Like so. But in theory, that's for our particular coordinate origin. That's the offset from an even spacing of the voxel cell dimension, right? So we know that this is the, the x displacement basically, like this is the offset that we would need to either add up to top ourselves off or subtract it away to get to the origin. So when we want to determine like what the min corner is, let's say we were doing the min corner off of just the origin P as opposed to using the camera offset. We do want to use the camera offset probably. But let's suppose we did. Then the min corner hot would just be whatever like 0, 0, 0 is minus that x disp, right? So it would subtract away that, and then we would be flooring to the voxel, right? And that's really all we would be doing. Unfortunately, we don't have a modulus operator apparently, which is news to me. So we need to kind of put this stuff in there. I think that's stuff that we will save till next time, and we'll go to a Q&A now. But that's basically it. Okay, good. So someone confirmed it was day 566, which is what I thought it was. And so I think that I just set the timer wrong or something. So wanted to get that corrected. You talking about non-realistic but good-looking art got me thinking. Do you plan on having game entities that manipulate light in extremely non-real ways? No. Uh, we could certainly play with it, but I had not really been considering any of that at the moment. It would be interesting to have entities that sucked light out of a room, potentially. That seems like it might be fun. I'm not sure about bending normals around. That sounds like I don't think humans would necessarily like that effect because they wouldn't know what to make of it. Probably it's a little bit too much, if that makes sense. Why not use mod directly? So the modulus this operator doesn't actually work for floating point, right? It only works for integer values, and if we're doing modulus on an integer, then yeah, I mean I could write it this way. And presumably the compiler is smart enough to do the right thing there. But again, I kind of want to think about what I want to happen when it's negative, and I need to think about a bunch of stuff. So I'm just going to write it like this for now and kind of remind myself to go in and figure out what I actually want to have happen. In terms of the floating point part, a floating point modulus you actually have to do, right? You actually have to implement that in float somehow. And in this particular case, because it happens to be a mod by 2, honestly, we could do some bit manipulation and do it if we wanted to. Because a mod by 2 just so happens to be something you could do more directly on the bit values. But I don't know that we really want to do that. I probably just want to implement a regular modulus, SSE modulus, that we just do like a floor subtract kind of a thing. So I don't anticipate doing that, but you know. Couldn't you contrive it so that chunk dim is always an even multiple of light cell dim? I certainly could. I could also do the opposite of that. And make sure that light dim is always some even proportion of chunk dim, right? And that might be smarter. You know, it's hard to say. Like we could just take whatever the size of the world dimension is, divide it by some known value that's the resolution we want. So we divide it by 17, or we divide it by 10, or whatever. And we say, all right, now it's just matches. In fact, yeah, now that you bring that up, that might be smarter, because then you don't have to worry about this anymore. That's a really good point. I don't know why I didn't think of that. I guess I didn't have peanuts for most of the stream. Culdeview, so are you asking basically like how do you write math stuff for people to understand clearly? Is that what you're asking? Rational Coder asks, I'm missing something fundamental about spherical harmonics. I get the idea of decomposing areas into spheres, but I don't get how you could use something like that to accumulate some representation of light that you could reconstruct. Would you be willing to provide an intro sometime? So I haven't ever worked with spherical harmonics, so I don't really feel qualified to give an intro, but what I can tell you to maybe help frame the understanding there, but you should go read about it more, is just that the idea of orthogonal bases for things in general is that they can be added. I mean, that's sort of why you use them in a sense. So, for example, if I take and I break down a light source, right, into a set of base light values that I know are orthogonal, right? So I know that they don't overlap, right, in any way. They're linearly independent of each other or whatever, right? Then I know that I can add those together like a normal vector space, and I know that I'm getting standard vector addition rules out of them, right? I know that all the things that I would want to do will work. I can scale them by a certain amount. I can split one into two halves and add them back together and get the same result, right? Split them into two halves, scale them, add them, and I get the same result as scaling the original, right? Like all the same stuff you would want to do in vector spaces. Spherical harmonics are an orthogonal basis in that regard, as far as I know. And so what that means is that what you have done when you decompose a spherical lighting, a set of spherical lighting samples, and you decompose them into basis functions that are the spherical harmonic basis functions, what you're basically saying is specifically that they do add to reconstruct the original, and it was an orthogonal decomposition so that if you want to add those parameters separately, they will reconstruct if you'd added the two lightings separately, right? And this is no different than any other deconstruction you normally use, like the discrete cosine transform, Fourier transform, Laplacian, like any kind of transform that you normally use, they all share this property. And that's the reason why we like them, right? The reason why people like these kind of transforms is specifically because if you have a transform that you just transform some values you need, you transform it, and then whatever you do in the other space wouldn't correspond to the same operations in the original space, it's really hard to work with that, right? Because if you have a nonlinear transform like that, then unless the whole goal of the thing was to do nonlinear work with it, then you end up with a problem of not being able to just say, oh, I want to add these two lights together. I just add their spherical harmonic coefficients together, whatever. Or I have the Fourier transform of these two waveforms. I can just add them together and I get the same thing as adding the two waveforms, right? That is typically why you want these kinds of basis functions. They are the basis functions which give you back useful operations. We can pick other basis functions all day long, but they won't have those same properties if we just randomly pick them. You have to specifically construct basis functions that have orthogonal properties if you want to end up with vector space at the end of it, right? Okay, so Culdeview says, yeah, essentially, or maybe anything with lots of jargon that's kind of essential to working with the subject seriously. I find myself on the other side a lot when I'm doing like FPGA stuff and I have no idea what people are talking about. But once I learn all the jargon, it becomes second nature to think about things in those terms, if that makes sense. So I guess what I would say is when you are explaining something, I think it's crucial to remember that what you are trying to do is form a picture in the person's head that works as a matter of course, right? At least this is how I think about it. Because you haven't really understood something if you only understand it in terms of the jargon. You only understand it if you understand it without needing the jargon. That's how I look at things, right? And as a consequence, it becomes pretty easy for you to know if your explanation actually is accessible to a beginner, because it should be possible to explain the thing without any jargon and just mention what the jargon is for the thing as you're explaining it, right? So for example, when I answer a question in the Q&A, I will often use jargon because they're brief answers, right? Like, to give a very specific example, I just used the word orthogonal in an explanation to somebody asking about spherical harmonics, but I didn't explain what orthogonal was, right? When I explain things on Handmade Hero the first time when we do something, I don't do that, right? If I say orthogonal, I then explain what does that actually mean, right? And usually what I see when I see math explanations is they're almost completely useless. So for example, usually you get this sort of thing, right? So if you look at this is a perfect example of a completely useless explanation. I would contend that there is literally no person on Earth, period, full stop. There are literally no people who don't already know what an orthogonal function is who could read this, right? Because there's nobody who knows integral calculus who doesn't know what an orthogonal function is, right? And right off the bat, you introduce all of this garbage, right? Which is like an integral of 3 functions. Nobody has told you what they are or how to think about them, right? With an integral right off the bat, you've got bracket syntax here, right? It just, forget it, right? It's just it's a nightmare, right? And this is how most math is. I don't know why. I have no idea why mathematicians tend to write this way, right? And similarly, like if you look at like something like the Fourier transform, which is like, you know, related here, I bet we can get another exact version of that, right? So this is completely useless. No one who doesn't know what the Fourier transform is will ever be able to read that equation, period. I guarantee you there is not a single human being on Earth ever in the history of time who didn't know what a Fourier transform was, read that and went, oh, I understand now. No chance. Zero. The only people who can use this equation are people who already know what the Fourier transform is and just need to remember what the equation is because they forgot or don't want to derive it or something, right? Like that's it, okay? Similarly, this stuff is also completely useless. F:(r) to c is completely freaking useless, right? It's not like, it literally, first of all, it doesn't save any space. I don't know why mathematicians write stuff like this, especially not for like in an explanatory text, right? Because if you just literally wrote out the words, a Fourier transform is something that takes real numbers as an input and outputs complex numbers, almost everyone who has had a high school math class would understand what you meant. Almost nobody who hasn't had graduate math has any idea what that is, right? At least not in the US. I guarantee you if I went to anybody who went to high school with me who didn't then go on to be a mathematician and I said, what does F:(r) C mean to you? They'd say, I have no freaking clue, right? And so the important thing is constructing the image in someone's mind. This is useless. This is talking to an expert. They already know what a Fourier transform is, so I have no idea why this is here. What you want to say instead is a Fourier transform is basically a function. It converts one thing into another thing. What are those two things? Well, the input to it is a real number. The output to it is a complex number. You remember what complex numbers are, right? A complex number is a thing that has a real number part, right? It's a regular number like 3.2. And then a complex part, that's something times I. Now, if you forgot what I was from your high school math class, I is the square root of -1. It might be kind of weird to think about what the square root of -1 is because it doesn't actually exist. That's why we call it an imaginary number. But actually, it's not so weird if you think about it. And the reason is it's not so weird is because, look, what if I wanted to, say I gave you a number, right? Any number, 7, right? And I said, take the square root of it. You know how to do it on your calculator, right? You know how to do it. You can just type 7 in its square root, and you even know what it means. It means that the answer that you get back, if you square it, you get 7, right? Everyone knows that. So you're like, what's I? I'm so confused. I don't get it. Imaginary number, I don't know. It didn't make sense in my high school math class. That's correct. It didn't make sense because high school math class suck and the textbooks suck. But it's not that hard to understand what it is. Now I give you a negative number. I said, can you tell me what the square root of -7 is, right? Well, you know what the square root of 7 was because you just did it. And so the only thing we really need to do, right, is we need to have a way of remembering that the thing was negative. Because when we square a number, right, if the thing that we square is negative, it just becomes positive, right? -2 squared is 4, and 2 squared is 4. So if I ask you to take the square root of 4, you can tell me 2. I say take the square root of -4, you're like, I know that it's still 2, but it's like gotta be negative. So all we were trying to do with that I is remember. We're trying to remember what the sign was. It's the thing that tells us what the sign was when we started, right? So you can actually get an intuitive understanding of what I is. It's the place that the negative goes when we square rooted because we need it to go somewhere. We need to remember, right? So we create an extra dimension to our number system to remember that sign. And that allows us more flexibility because now instead of when you ask me what the square root of -7 is, and I say I don't know because it can't exist, right? I say, I can tell you what the square root of 7 is, and then I can use an extra piece, I can add a piece to my representation of numbers to remember whether it came from a negative number to begin with, right? So that's what we're going to do with the Fourier transform. When we do that transform, we can think about that I that we need there. It actually has some meaning. It's not purely imaginary. It really does have some connection to reality if you think about it. There's ways we can connect it back, and that's one of them. So a Fourier transform is one that's going to take in a regular old number, the kind you're used to, and it's going to turn it into a complex number, which is maybe a number you're not quite so used to, but that number's not that complicated. It's really just the same as a real number in some sense, with that extra dimension added so that we can understand a wider range of source for our numbers, okay? So, when we take the Fourier transform, what we're going to do is we need to turn something into, excuse me, we need to turn something from the basic old boring variety that you're used to, right? The Euclidean space as you're usually used to, which is just a thing where, you know, it's like the world around us. We walk in one direction, we go straight. We walk in another direction, we go straight. We start putting coordinate systems on these things. We're talking about these like perpendicular lines, right? That are just like rulers going in directions, and that's how we think of our coordinate systems, right? But what a Fourier transform does is it asks a different question. It's saying, what if we wanted to represent where we are in a space, or what the value of something is, with basis functions that aren't just little rulers, right? They're actually sine waves. They're actually waveforms, things that oscillate, right? And so rather than you just thinking about as I turn a number up in my coordinate system, as x gets higher and higher, I'm just going further and further along the x-axis. Rather than thinking about that, what we need to think about is as I turn up my number x, it does get higher, yes, but then it starts to get lower again. And then it gets negative. and then it comes back up to positive, and then it goes, right? So it's oscillating, okay? And so what the Fourier transform does is it tries to take values that we were previously maybe representing in some other space that was actually like just representing things as little rulers, and we're trying to then turn it into something that is represented by sine waves, adding these sine waves together to reproduce the result, right? So the basis functions, the output of a Fourier transform, is a representation of the input that's made using sine waves, which is kind of a weird thing to think about. But if you think about the kinds of things that we need, and I could keep going on about this, but you get the idea, right? So does that give you some perspective? I could keep going and talk about how, all right, how do we start making sine waves that cancel each other out so that we can have the same sorts of things that we want to have with a vector, right, blah, blah, blah. That's how you explain something, because now someone has something in their brain that they can actually think about when they're thinking about a Fourier transform. Instead of this, which is nothing, there's nothing in here to think about. It's just purely abstract, right? There's nothing to hold on to. You're just floating in space, and this is the way math things often look, right? Let's see. Rationalist, thanks. I guess I put too much emphasis on accumulation and reconstruction. I can understand about what you just said about orthogonality addition. My misunderstanding is more fundamental. I understand how you can use ray tracing to get light intensities and colors at probe points, which can be passed to your fragment shader, but I don't get how you can get some spherical representation of light at probe points and what the heck your fragment shader would do with it. So again, if we're talking about spherical harmonics, so spherical harmonics are a series of lobe shapes, right? Much like the Fourier transform is a series of sine waves that just are linear, or in time, right? Like we think of an audio waveform for a Fourier transform, let's say, right? We are just taking a chunk and we're going to pretend that it's periodic, so it's just infinitely repeating, because that's part of the definition of how the Fourier transform works. If you need the Fourier transform to operate on a finite window, it's actually kind of wrong, right? But we're going to add a bunch of sine waves together to reconstruct some arbitrary signal that we had, right? And you see this in the Fourier transform. The graphic equalizer on your stereo is a Fourier transform of the sound wave, right? A very low resolution Fourier transform. It's showing you the various frequencies that you would add together to get back the sound wave. It's just, instead of showing you the actual number you would need to reconstruct it, it's showing you an average of those binned into 6 buckets or 5 buckets or whatever, right? So spherical harmonics is the same way. It's saying, look, let's do basically the Fourier transform on a sphere. And so instead of each thing just being a sine wave, it's actually like a sinusoidal lobe. And if we imagine taking any sphere with any number, any amount of data on it, just like the Fourier transform says that with an infinite number of sine waves, we can reconstruct an infinitely precise signal that you input, the same is true of the sphere. A infinitely large number of spherical harmonic coefficients can reconstruct any spherical information, right? So we are never going to use infinite, but if we use enough, we can reconstruct the sphere of lighting from our spherical harmonic coefficients. And if we can reconstruct the sphere of information, then when we actually need to do our lighting is just a series of questions about what is coming in from a sphere, right? That's what light is off of a surface. It's a BRDF or any kind of like lighting transfer function is just saying for some output direction, I need to do some summation over the sphere of different, input directions, and that's how much light goes out, right? And so as long as the spherical harmonics can reconstruct the data of the sphere, it's pretty easy actually, because you just ask the spherical harmonics anytime you want, what's the lighting in this area? And it tells you, right? The same way a Fourier transform can reconstruct a particular part of a signal, the spherical harmonic coefficients can reconstruct a particular part of the sphere and how bright it was at that point. And so that's fundamentally all you would be doing with spherical harmonics, right? All right, that's the end of the cues. All right, thank you everybody for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always. I am in the process of collecting some questions because I'm going to be doing a little bit of tutorial video series at some point here soon in the future. And I'm collecting questions that are, I would say, generally applicable novice questions, was sort of what I'm trying to get a collection of. And I've gotten a ton of emails. I don't, it might even be over 100 at this point. But I basically asked the question on Twitter, loath as Twitter may be. But here is the specific tweet that I'm talking about. But I said, dear aspiring novice programmers, what programming concepts, techniques, or processes do you most want explained and tutorialed? And I said, just mail them to fac@mollyrocket.com. And I've got like just tons and tons of responses, which is great. So I'm kind of going through and collating all of those and planning exactly how I want to do them. But if anybody wasn't aware of this, I feel like I should mention on the stream a few times just so people who maybe don't read Twitter, which honestly should be pretty much everyone at this point because it's a terrible platform, go ahead and email me your questions there if you have some that you think would be appropriate, or even if you think that they're, if you don't know, because I can always I'll be like sieving them into things I think will work well and things that I don't. So you don't really need to censor yourself. Just if you think you have a question you might want to ask, you can send it in and I'll deal with it. The reason I bring that up is because during the pre-stream we had a good one, which was pointer aliasing. It's something a lot of novice programmers don't know what it is, but they probably have heard of it and they aren't sure whether they should care or what it would mean. And so pointer aliasing is a good example, and I'm going to add that one to the list because I'm going to probably want to make a specific video that's like, what is pointer aliasing and why you should care. So if you have some of that stuff that you think you might want to know about yourself, that you think would make a good topic as sort of a standalone piece that just says, here is a self-contained like 15-minute video explaining X, that is exactly what this project is about. So do send those to faq@mollyrocket.com. And more broadly, if I get them on stream, I'll also try to remember ones that I think would be good for that. But I do kind of use the number of times that a question is asked as sort of a little bit of an impromptu vote on which ones I should prioritize covering, because they're the things that more people are confused about or more people think they want to know about and might spend time to learn about. So do send it in, and that way it kind of will count as part of that vote as well. All right, that's it for today. I'll be back tomorrow when we're going to finish doing the sort of voxel, large, small voxel work. And that's really my goal for the weekend now. I think that's in good shape. I'm glad we thought of that stuff today. I think that's a good way to do things, and I'm excited for that going forward. So hope we can get that finished up tomorrow, same time, same place. And then next week we can start to focus on light transport and working that through. And then, we're getting closer. We're getting closer to having a really good lighting solution, which is really where I want to be. Lighting is very difficult, and so getting a good lighting solution in place is an accomplishment we should give ourselves a pat on the back for. All right, that's it. If you want to follow the series at home, of course, you can always go to handmadehero.org and pre-order the game. It comes with a source code, so you can compile it yourself on your own machine, play around with it. If you would like to finish the voxel work before I do, it's a good exercise to do. It's pretty straightforward, so maybe give that a shot. and then tune back in tomorrow, and I will do it myself. Until then, have fun programming, everyone, and I'll see you all on the internet. Take it easy, everybody.